Some metals are stronger than others. When put into a solution of another metal ion, the metal ion can take electrons away from it. Let's look at three different situations. So in the first situation, we take a strip of zinc and we put it into a zinc solution. So this could be zinc nitrate, zinc sulfate. The nitrate or the sulfate, the anion, it is a spectator. So we go ahead and eliminate it from the reaction that will occur. So what will happen is the zinc ion, the Zn+2, will go up and tug on the electrons on the zinc metal. Because they're the same strength, it can take those electrons away, but in return, zinc atoms would be deposited. So the result is nothing really happens. So you stick it in there and there can be an electron exchange, but because they're the same strength, you're really not going to see anything happen. Let's look at the second situation. So in this situation, I have a piece of copper metal instead of the zinc. And when I put that copper metal into that zinc nitrate solution, the zinc goes and tries to tug on those electrons in the copper to try to take them, but copper is too strong. And so as a result, there's no reaction. Nothing happens. Let's look at the third situation. So this time I have a solution of copper 2 nitrate, and I put a strip of zinc in there. And immediately, within less than a second, that zinc strip has a little bit of black stuff that forms on it. That is the copper that has formed. So what happens is the copper ion, the Cu2+, it comes up and it tugs on those electrons and it wins those electrons. It takes away 2 electrons from the zinc and it makes copper metal, which is that a black stuff that will form. The overall reaction is right here. So the zinc is going to lose electrons and the copper ion is going to gain them. And I can write the reaction in 2 steps. So the first step is that zinc is going to lose 2 electrons. And when it does that, I will get zinc ion. And that will just go into solution. And I can draw it in there. Zn2+ will be formed and floating around in the solution. The second half of the reaction is copper is going to gain those electrons, copper ion, copper 2 ion. And so I will make copper solid. So I take one solid that loses electrons, and then I take an ion that gains those electrons and becomes the solid. So this is a redox reaction. And in this first step, because zinc is losing its electrons, this is an oxidation step. This is a reduction step because the copper is gaining. Now overall, I can add them up. And when I add them up, their electrons will cancel. And I will get zinc solid plus my copper 2 ion. And I'll get my zinc ion and my copper solid. All right, so this is a redox reaction. We can see the electron exchange, and we see that a reaction occurred because I have a black stuff that formed on that metal strip. And if I were to allow it enough time, that black stuff would actually be copper colored because this is copper that is being formed. Well, in 1800, Alessandro Volta, an Italian physicist, he invented the first battery, and it was called a Voltaic cell. And instead of the electrons being exchanged through direct contact, Alessandro Volta, he separated out the oxidation and the reduction step. And today we call these batteries. This is a spontaneous process. When you have a metal ion that is strong that can pull electrons off a weaker metal, if we separate the steps, those electrons traveling from the metal to the powerful ion, we can light a light bulb or measure the charge of how many electrons are going by. So essentially we're making a battery. So let's look at the steps of our voltaic cell that Alessandro Volta invented. So in one beaker, I have a solution of zinc sulfate, and the sulfate is not going to do anything. And then in another beaker, I have a solution of copper 2 sulfate. Again, the sulfate is a spectator ion. So notice that I put a piece of zinc into the zinc nitrate solution. And so nothing will happen because the zinc ion and the zinc piece of metal, they're the same strength. And I do the same thing over here. I put a piece of copper strip into the copper ion solution. So these pieces of metal, they're called electrodes. And I'm going to connect the electrodes with a wire. And our wire is hooked up to a voltmeter. I also could hook it up to a light bulb, say, and I could power a light bulb. I also need to complete the circuit by using what's called a salt bridge. So this is my salt bridge right here. It is something that contains ions that can move between beakers. Standard concentrations of solutions for both the zinc sulfate and the copper 2 sulfate solutions in each of the respective beakers, they are 1 molar concentrations. And this is at room temperature and at atmospheric pressure. In your homework packet, you should have a paper that has a list of reduction potentials. It should be the first couple pages of your homework packet. These reduction potentials, they tell you how much energy each of these half cells can generate. So in other words, I can quantify how much energy this zinc cell can generate and how much this copper cell can generate. All of the different scenarios are compared to a hydrogen half cell. So the hydrogen half cell is defined as having 0 volts. And so everything is compared to that hydrogen. And we can generate a list of reduction potentials. Okay, if you memorize everything here on this slide, you're going to be in good shape for the homework and the test. So you need to understand what's here. So we can quantify each of the beakers. One of them is going to be the anode and one of them is going to be the cathode. How you determine which one is the anode and which is the cathode is by looking up their reduction potentials. So let's first look at our zinc cell. So looking at your reduction potential chart, we find zinc is this equation with a voltage of negative 0.76 volts. We also can look up the copper half cell, and there are several coppers, so make sure you pay attention to which one we have. And this one we have a +2 ion, and it's going to the metal. So on our chart, it's this equation. And it has a voltage of a positive 0.34 volts. So you look up what's in the beakers on your chart and look up the voltage. The one that's the weakest one, which is our zinc, is actually going to run backwards. So you're looking at a list of reduction potentials. There is no list of oxidation potentials, but you cannot have reduction without oxidation. So from the reduction potential chart, you need to pick your oxidation step. The oxidation step, that is going to be the weakest one, the one that has the lowest voltage. And in this example, my voltage just happens to be negative, but it is possible that both the voltages could be positive, and you would have to just, again, pick the lowest voltage. So notice that in this equation, I wrote the equation flipped, or I wrote it the reverse reaction. Because I can't have reduction without oxidation, I have picked the zinc as my oxidation step. So I need to write it as an oxidation step where it's losing electrons. So I just look up the equation, find the weakest one of the two, and then I write it backwards. When I do this, I have to change the sign of the voltage. So instead of a negative 0.76 voltage, I now have a positive 0.76 voltage. This one over here is going to be the same. It is going to be our 0.34 voltage. All right, so we picked our oxidation cell. In this picture, it's on the left-hand side, but it is possible you could have a picture where it's on the other side. How you determine which one is the anode or the oxidation cell is whichever one has the weakest voltage on your chart. So notice that anode and oxidation go together. And how I remember this is they both start with a vowel, so an A and an O. Let's look over at our cathode. So our cathode is our reduction cell. It's the one that we just keep as is from our chart. And notice that they both start with a consonant. So anode goes with oxidation, cathode goes with reduction. So in your anode and your cathode, the electron is going to travel. It always starts where the anode is, and it's going to go over to where the cathode is. So you can remember this direction. I always remember that it goes in alphabetical order. I go from the anode to the cathode, from A to C. Now that salt bridge, this glass structure right here, it is going to complete the circuit. So as one electron goes from the anode to the cathode, now this cell becomes negative, and this cell over here becomes positive. The ions in the salt bridge, they're going to be attracted to that. So I'm going to have a cation come and enter into this cell, being attracted to the negative charge there. And I'm going to have my anion travel to this cell from the salt bridge into the solution because it's attracted to the positive nature of that beaker. So this will complete the circuit and allow more electrons to travel, because as soon as that ion comes in, both of the cells, they are neutral. So this is a continual process. An electron comes over, a cation is attracted to it, the anion is attracted to the other one, and then we can start over again with another electron being pulled over. And it's being pulled over by this copper 2 ion. That copper 2 ion will come and it will accept the electron and it will deposit onto this copper electrode. And my electrode will get larger. On the other side, the zinc electrode, because it is losing electrons, it will get skinnier and skinnier as it loses electrons, and we have zinc ion going into solution. Overall, in my anode, it loses mass of the electrode, and over on my cathode electrode, it will gain in mass. So I don't just have the zinc metal disappearing. It's actually just making zinc ion. And I don't just have copper atoms appearing. It's coming from those copper ions that are in solution. Now, how much energy can I generate from this cell? Well, you're going to add up your voltages. So I have the voltage of the one that I changed the sign, and then I have my other voltage that I just added, that I just looked up, and I'm going to add those up. So my total voltage I'm going to get is 1.10 volts. And this is a positive number. This is a spontaneous process anytime we have a positive voltage. Another way to represent the voltage is by using an E. So my E is a voltage of 1.10 volts. In other words, for a zinc and a copper voltaic cell system, my voltage that I will generate is 1.1 volts. So here's another picture that can see the same process occurring. This time we see that there is a light bulb that's hooked up. We see a picture of the zinc anode. We can see how the atoms are becoming ions and going into solution, so that electrode is getting thinner. And then you see on the copper electrode that those ions are becoming atoms. We can write their half reactions right here. Again, those are looked up, so you can just look them up on your chart. Remember, this is the one that runs backwards. This is our oxidation step. Here's yet another picture that shows the same thing. You can see that my electrodes right here, it's quite dramatic how this electrode has gained in mass, and this electrode over here has lost mass. And we've gone through these half reactions. Again, this one is written backwards, this one is written as is. And I can add them together so those electrons cancel, and I get the overall cell reaction with both my oxidation and my reduction half steps added together. Because again, you cannot have oxidation without reduction. So when we say the anode loses mass, where does that mass go? Remember, it goes into solution. And when we say the cathode gains mass, where does it get that mass? Well, it comes from the solution. So I'm not just having mass appear and disappear. It actually is coming from somewhere. We do have conservation of mass. So I can't emphasize this enough. Electrons always flow from the anode to the cathode. And I've already gone through this step, but let's go through it one more time. So again, you'll look up these values in your packet. You're going to evaluate which one is the weakest. The weakest one has the lowest number. You're going to write that one backwards. And when that happens, you're going to switch the sign on your voltage. Then you can add up your 2 half cells to get your total reaction and to get your total voltage, 1.10 volts. So this voltage could have different abbreviations. It's also called an EMF, an electromotive force. It's also called the voltage. It's also called the electrical potential. And it also is given this little symbol of an E naught. And again, a positive voltage equals spontaneous. So if you get to choose which one is the cell that you flip, you're always going to flip the weakest one. And then you'll always get a positive voltage. If you flip the wrong one, or somebody has flipped the wrong one and wants you to calculate the voltage, then you're going to get a negative voltage, and that will not be spontaneous. Your list of reduction potentials is also called an activity series because I have some metals that have a greater reactivity than others. There is a shorthand notation for these voltaic cells because it's kind of clumsy to have to draw the beakers and the electrodes and the salt bridge. Some of the parts for this that you want to remember is that they should all be in solution. So you should have some sort of representation that there's a liquid there. You should have your electrodes in the solution. They should be connected by a wire here. And you should also have a salt bridge that is completing the circuit that is submerged in the solution. And remember, in this, if you identify the anode and the cathode, the electrons always go from the anode to the cathode. But again, this is kind of cumbersome to have to draw this big picture. So there is a shorthand notation that you can do. So for this overall reaction of, again, copper, iron, and zinc that we've been working with, I can draw this shorthand notation. So what are some of the patterns? In the equation, I look and I go from atom to ion and ion to atom. I always have my oxidation step first, or my anode step first, and then my cathode or my reduction step last. And you just use the balanced equation to help you. So again, it goes atom, ion, ion, atom. So I can see that it goes from atom to ion. And so I can draw my salt bridge, which is those 2 double lines there, and then say my zinc goes to my zinc 2+. So that's my oxidation step, or my anode. You always want to write the anode first. And then using the equation again to help guide you, this goes from a +2 to the atom. So again, I do ion, atom. This is my reduction step. This is my cathode. So you also need to get used to the shorthand notation, and you should be able to go from the shorthand notation to the equation, or the equation to the shorthand notation. All right, let's look at this one. Write the shorthand notation for the following reaction. What voltage is produced, and will this be spontaneous? So in this case, I do not get to choose which one I reverse. So I'm going to look at my reduction potential chart and look up those charges. And so I know one of them is going to be flipped and one of them is going to be as is. So let's go ahead and split these up. So I have an ion going to the atom. And I do have some electrons here, but I am not going to bother with them. I can't fill them in. But I'm going to look at these 2 half reactions and then compare. So looking at that first one, the iron ion to the iron atom, I see that it looks exactly like the one on my chart. And my chart says this is a minus 0.44 volts. Okay, so this one they didn't flip, it's as is. And then I'm going to look at my next one, and I see that on my chart, it says that I have a nickel ion going to nickel, and it has a volts or an EMF of a negative 0.25. So that's what it says on my chart. So comparing to what I have from that bounce equation, I see that this is the one that they flipped. So this is the one that they reversed. So the volts of this one, as written, are a positive 0.25. So they were being very silly and they flipped the wrong one. They should have flipped the negative 0.44, but they didn't. So this is how it is. So I'm going to add this up to get my voltage. And I see that I get a negative 0.19 volts. So this is non-spontaneous. Why? Because they flipped the wrong one. So when they write it in an equation, you don't have a control of which one they changed, okay? If you're just given two beakers and you can choose which one to flip, always change and reverse the weakest one, the one with the smallest number. So let's look at this next one. I have iron going to my iron ion, and then I have my copper going to my copper atom. And again, you'll look this up. So on the chart, it says that I have this reaction and the voltage is a negative 0.44. In fact, we used this one in the previous example. So you can see that this is the one that they flipped this time. So I'm going to go ahead and change the sign because this is the one that they're choosing as the oxidation half step. So it should have a positive 0.44 now. Okay, so this is the one they reversed. So on the next one, this one is going to be as is, and the chart says that the copper 2 plus goes to the copper with a voltage of a positive 0.34. So again, we change one and the other one stays the same. And so I can add this up and we see that we have a 0.78 volts and it is a positive charge. This one's going to be spontaneous. So when you don't get to choose, you just have to change the one that they changed for you. And if you get a negative number, you know it's non-spontaneous as written.